Friends, we shall continue with the study of dynamic equivalents or large scale systems. So far we have studied the basic concepts of dynamic equivalencing, and also we have learned about an algorithm which can be used for identifying the coherent group of generators. Now, the next step will be that we have to do network reduction, right, and then aggregate the models of the generators which form a coherent group. That is, when I say that if we have once we have identified the group of generators which belong to one coherent group, then these generators have to be replaced by an equivalent generator. Okay. Therefore, the first step is that we have to first do network reduction. Okay. Now, for performing this network reduction, let us again look at the definition of the coherent group. Our definition shows that a coherent group of generating units for a given perturbation, I am emphasizing this word given perturbation, is a group of generators oscillating with the same angular speed and with terminal voltages in a constant complex ratio. Therefore, we will make use of the definition of coherency to do network reduction. Okay. Now, here there are two aspects. One is that the machines in the coherent group will have same angular speed, and second is that the terminal voltages of these machines will be in a constant complex ratio. Okay. Therefore, for network reduction we will be using the second important component of this definition. Okay. What we really do is that you have say group of machines which are coherent, okay, and they are connected to their own individual buses. Therefore, now what we have to do is that we have to reduce the number of buses and retain only one bus, so that all the machines which are coherent are connected to one bus. This is what is the main thrust of network reduction. Now, to illustrate this concept, what I will do is that we will consider that a system which has say n generators and n buses. Okay. And let us say that the generator n minus 1 and n, they form a coherent group. Okay. Just to start with, actually we will take that the two generators which are numbered as n minus 1 and n, they form a coherent group, and we will replace the two buses, bus number n minus 1 and bus number n, so that we will reduce the number of buses. Okay. Now, in this process what is normally done is that we retain one bus of this group with the same voltage. So, different buses will have different voltages, right. Therefore, let us say that we retain bus number n minus 1 and the voltage of that bus will be retained as it is, right. Therefore, when we do this simplification or network reduction, let us see that what will be the changes in the network model. Okay. Now, to perform this network reduction, we will use this condition, that is the voltage of nth bus and voltage of n minus 1th bus, right. The rest of these two voltages is a constant equal to B, and this B is a complex number, that the voltages maintain a constant complex ratio. Okay. Therefore, we will make use of this condition. However, we all know that for identifying the coherent group of generators, we have used this first condition. First condition, that is delta n minus 1 t minus delta n, that is the for all time instants over the complete period, right. The two swing curves are identical if this difference is a constant and it is less than some tolerance. Literature survey shows actually that the tolerance of 4 degrees or 5 degrees has been considered. Therefore, now we will use this condition to obtain a reduced network. Okay. Now, when you obtain the reduced network, the process is very simple. We start with the actual network model. Let us say that this is the network model, that is I is equal to summation of j equal to 1 to n y I j v j, right. This forms our steady state network model, where I is the current injection at bus I, V j is the voltage of jth bus, okay, and y I j are the elements of Y bus matrix. Okay, it is very straightforward, this is no problem. Now, in this, when you write, actually you will have say n equations, when I is varying from 1 to n equations you can write down. Now, in these n equations, wherever you have V n, we can replace this V n by B into V n minus 1. Okay. Now, if you perform this exercise, let us say what type of equations we will get. We will let us write down I 1 can be written as y 1 1 V 1 plus y 1 2 V 2 y 1 n minus 1, write up to n minus 1 term first, n minus 1 V n minus 1 plus y 1 n, voltage is now replaced, V n is replaced by B times V n minus 1. Okay. Therefore, this equation now can be written as I 1 can be written as y 1 1 V 1 plus y 1 2 V 2, last term will now be equal to y 1 n minus 1 plus B times, B is a complex number, into y 1 n into V n minus 1. Okay. Therefore, when I replace the voltage of nth bus by B into V n minus 1, I get the equation for I 1 as y 1 1 V 1, y 1 2 V 2, and the last term will now be the y 1 n minus 1 plus B times y 1 n into V n minus 1. Therefore, what I see here is that now in this in the Y bus of the network, right, the last column, first thing is that this Y bus is going to n minus 1 into n minus 1 now, and the last column is going to be different. Otherwise, y 1 1, y 1 2, these elements up to y 1 n minus 2 they will be same. Okay. Now, similarly you can write down for all the buses. Okay. Now, suppose now I write down for say corresponding to n minus 1th bus. Let us write down the equation for n minus 1th bus, that is you can write down here. So, let us write down the current injection will be I n minus 1. Okay. This will be now y n minus 1 V 1 plus, I am not adding these terms, let us write down this last term here, plus what will be this thing? Now, you will have here y n minus 1, what is the value of now this one? N minus 1 plus y, that is what plus, I am just putting b after plus y n minus 1 is going to be y n minus 1 n into b, and this sum multiplied by v n minus 1. Okay. Now, you write down the last term, that is I n. I n will be now y n 1 v 1, that is around the last term here, y n n minus 1, okay, plus y n n into b into v n minus 1, okay, because v n is replaced. It is very simple. Now, the number of equations still are equal to n, although the number of elements in the row have been reduced from n to n minus 1. Now, what we do is that we add these two equations, but before addition what we do is that you multiply this I n by b star. I will tell you why we do this, but you multiply this I n by b star and add these two equations, and we will call this by the symbol I e as I n minus 1 plus b star, that is b star stands for complex conjugate of b into I n. That is on this left hand side. When I perform this addition, that is I multiply this equation, last equation, by b star, add it to I n minus 1, right, then I get on left hand side a current term which is I n minus 1 plus b star I n. Okay. Then you can write down I e equal to, I will write down only two terms, let us say I e will be equal to y n minus 1 plus b star y n 1, this multiplied by v 1. Okay. The last term we can be written here as then the term that you can write down here as y n minus 1 n minus 1 plus y n minus 1 n into b plus b star into y n n minus 1 plus b star y n n into v n minus 1. Okay.
B will with y n n, B star y n n into B.
B star y n n into B, yes, very correct. If it is going to be, I will put B here, B into B star y n n. Okay. Therefore, now what we have obtained is the n equations, not I am sorry, n minus 1 equations. That is number of equations which we were having earlier were n. Now we have reduced them to n minus 1 equations. Okay. And in the last equation, that is the n minus 1th equation, current injection IE is equal to I n minus 1 plus B star I n. Okay. Now, to understand why we have done this particular operation, multiplied by B star and added to the term I n minus 1. Now, let us see what is the complex power injection at n minus 1th bus by doing this equivalency. That is, the voltage is V n minus 1. If you multiply this by I e star, what does it show? This product shows the complex power injected at the equivalent bus. Okay. Now, this can be written as V n minus 1 into I n minus 1 plus B star I n whole star. If you expand this term, then it can be written as V n minus 1 I n minus 1 star plus V n minus 1 B I n. Okay. What does this expression represent? What does this expression represent?
Vn.
It represents the sum of the complex power injected in the original network at n minus 1th bus and at nth bus. Therefore, by doing this operation, we are retaining the total complex power injected at n minus 1th bus equal to the total complex power injected at n minus 1 and nth bus. So, this is a requirement actually, because when we are trying to reduce the network, we have to ensure actually that this condition of power invariance is maintained. Okay? And that is why we have performed this operation here, where we multiply this last equation by B star and add it to the equation corresponding to n minus 1th bus. Okay? Therefore, with this operation performed, we get now the reduced network. It has now n minus 1 buses, okay, and therefore I can write down the equation of the reduced network or the reduced network model as II equal to Yij Vj j varying from 1 to n minus 1. j equal to 1 to n minus 1. Okay. Now, this Yij, this bus matrix, which is n minus n, the dimension of this Y bus is now n minus 1 into n minus 1, and its elements are modified with respect to the elements of the original. Okay. This is the first step, which is called the network reduction. Now, in case suppose you have instead of two generators which form a coherent group, suppose there is one more generator which forms a coherent group, you can perform additional similar operation, and you can keep on reducing the number of buses, right. And while doing this network reduction process, what is to be done is that we retain the voltage of one of the buses at the original level. That is, when I have done this reduction process, the voltage of n minus 1th bus was retained, right. But suppose you have instead of two machines, you have suppose say 4 5 machines which form a coherent group, then you can select one of the machine bus and retain that bus and its voltage, right. So, that now what we can say that we have a network where equivalent machine is connected to the bus which is retained, and the equivalent machine we have to find out what will be the parameters of that equivalent machine. Okay. The network reduction part we have seen is a very simple process that can be done. Now, in order to obtain equivalent model of the machine, okay, first we will consider the classical model of the machine. That is, let us say that we represent the generator by a classical model, and then we will find out actually that what will be the equivalent machine which will represent the classical model of the system. I think this point is already covered. Now, to obtain the equivalent machine, we again look at the dynamic model of the system. The dynamic model of the system is written in this form, that is, for ith machine d delta I by dt is equal to omega I minus omega naught, which can be written as, if you use in per unit system or the speed is represented in per unit, this can be written as delta omega into omega naught. Okay. D omega I by dt equal to 1 upon m I p m I minus p, okay, where these terms are appropriately dimension. There is a dimension of all these terms have to be appropriate, that we all know it, there is nothing. Now, here is the very important point, that if I represent a generator by equivalent, okay, therefore, we know that the generator model considering the classical representation is of this form, that terminal voltage V I is equal to internal voltage E I minus Z I I I I. This is what is the classical model for a synchronous generator. That is, the terminal voltage is equal to the internal voltage minus its own impedance, that is the impedance behind I am sorry, the impedance which is equal to Z I I. In case you neglect the resistance, then this becomes the subtangent direct axis subtangent reactance. Okay. And the power injected is the real part of E I star into I I. This is just to repeat, actually there is nothing new, this we all know it. Okay. Where our definition for this Z I I is R I plus J times x d I prime, E I is magnitude E I angle delta I, P M I is a constant, and the magnitude of E I is also constant, because it is a classical model. Right? We represent the generator by constant voltage behind direct axis tangent reactance. Now, here to obtain the equivalent, let us first write down the two equations using the original voltages for the machines n minus 1 and n. That is, if I write down for machine number n minus 1, right, I can write down E n minus 1 there is a voltage, right. This can be written to be equal to V n minus 1 plus impedance of this machine, right. Now, let me call this as a, the different symbols are used, but I will use I to show that it is the internal impedance Z I n minus 1 into I n minus 1. That is, let us look actually that system is not reduced, we have actually the n machines, okay. And then the equation of the classical model looks like this, that the internal voltage is equal to the terminal voltage plus this drop. Similarly, I can write down for nth machine as V n plus Z I n I n. Now, what should be the next step? Because we have these two equations, and one condition which we know is the relationship between V n minus 1 and V n. We can use that relationship. So, that in this equation what you do is you first, let us first replace V n by B times V n minus 1. So, that you can write down this E n equal to B times V n minus 1. This term remains same. Okay. Now, you divide this equation, I will call this equation just for reference A, and I will denote this equation as B. Okay. You divide this equation A by Z I n minus 1 all through. So, that you can write down now E n minus 1 Z I n minus 1 equal to V n minus 1 divided by Z I n minus 1 plus I of n minus 1. Okay. For the second equation, we can write down E n divided by Z I n equal to B times V n minus 1 divided by Z I n plus I. Okay. We shall number this equation as C, okay, and number this equation as. Okay. The next step will be that you multiply this equation D by B star and add to equation C. Okay. Then what will you get now? When you do this operation, you will get E n minus 1 divided by Z I n minus 1. This remains same. To this we are adding a term. I am multiplying by this by B square, the whole equation, that is B star, not B square, B star. Put E n divided by Z I n. Okay. On the right hand side we will get Rajesh, that is this second equation I am multiplying by B star and I am adding it to equation C. Now, this comes out to be equal to V n minus 1 divided by Z I n minus 1, okay, plus B star B V n minus 1 divided by Z I n plus I n minus 1 plus B star I n. Okay. Therefore, next what should we do? This is okay. I n is multiplied by B star.
Last it is IB is written, that should be B star. IB star into IN now.
This term.
And that is only B star only.
Here.
B star into IN.
Last.
Last term.
It is written IB star, it should be only IN.
Just right.
In place of IB star, that is only B star.
अरे वो बी है बस समझ लो यार.
See here, this is our equation which remains as it is. Okay. To this I am multiplying this the whole equation by B star. So, that the first terms okay, B star E n by Z I n 1. Here I have not multiplied here V n minus this V n minus 1 upon Z n minus, this remains same. Here B star into B V n minus 1 upon Z I n, right. Here I n minus 1 as it is, plus this is multiplied by B star into I n. What is the problem?
Sir, IB star is written, that should be B star only. Because there is no current IB star.
Aha, oh, this is side mistake. This is to be called as B star, okay. And this is just a slip. Okay. Now what we can do is here, we can easily see one very interesting thing here, that this is the equivalent current. That is the equivalent current that is to be injected at the particular bus V n minus 1. Therefore, now we can write down this whole thing. This whole thing can be written as we write down this first this term V n minus 1, I take it out. Okay. Then coefficient of V n minus 1 we can write down here as 1 upon Z I n minus 1 plus B star B divided by Z I n, okay, plus I e plus I e equal to this term E n minus 1 divided by Z I n minus 1 plus B star E n Z I n. Okay. Now, the equivalent generator equation, if you write down the generator equation of the equivalent generator, then the equivalent generator equation is written in the form V n minus 1, okay, plus, let me write down Z equivalent, Z is Z E into I E must be equal to E equivalent. That is, if I try to write down the equivalent generator, the equivalent generator internal voltage is E E, equivalent impedance is Z E and equivalent current is I E. Therefore, equivalent generator model when I put in the classical form is V n minus 1 plus Z E into I equal to I. Okay. Therefore, now you can identify from this equation what is this Z E and what will be the E E. Z E can be simply obtained because you divide this whole equation by this coefficient. So, that write down V n minus 1 is equal to this reciprocal of this plus I E plus equal to reciprocal of this term into this whole thing, and therefore, the Z E can be identified, that is the equivalent impedance Z E, equivalent impedance Z E can be identified as 1 upon Z I n minus 1 plus B star B divided by Z I n inverse, right, and equivalent voltage, internal voltage E E is identified as 1 upon Z I n minus 1 plus B star B divided by Z I n inverse multiplied by E n minus 1 divided by Z I n minus 1 plus B star E n divided by Z I n. Okay. That is, you can see that all the terms on this side of this equation are known to you, because the generator, equivalent generator is obtained by replacing the two generators, one corresponding to the bus n minus 1, another corresponding to bus n. And in the equivalent generator, what we have done is that we have retained the voltage of n minus 1th bus intact, right. What we have done is that we have obtained what should be the equivalent impedance and what should be the equivalent internal. Now, suppose now instead of having one machine, two machines forming a coherent group, if we have more than two machines, then this process can be repeated, and once you repeat this process, actually you can get the equivalent generator representing the coherent group. Therefore, this exercise has to be done. Now, so far what we have done is that we have considered the classical model, but suppose if I do not want to go for classical model, if it is a classical model, then in this classical model actually I am not representing the excitation system, I am not representing actually the synchronous generator dynamics or stator equations in that form, right. We are assuming that the flux linkage is constant, okay. That is what is the classical model. but in case you want to have more detailed representation, right, then the procedure is that you replace each component of the synchronous machine by equivalent. That is, what is to be done is you replace the turbine governor models, that is each machine has a turbine governor, and suppose there are few machines which are part of the coherent group, then you have to obtain an equivalent turbine governor model. Okay. Now, for obtaining the equivalent turbine governor model, the procedure is very simple, because here the machines which are coherent, all the machines have the same rotor speed. Okay. Therefore, if I look actually the turbine governor model, then input is speed deviation and output is the mechanical power output, is it not? Therefore, each of the turbine governor model input is delta omega, because speed deviation is same for all these machines, and therefore, the total mechanical output I can get simply by adding all the transfer functions, because total mechanical power will be equal to the transfer function of machine 1 plus machine 2 plus machine 3 multiplied by delta omega, right, and therefore, these transfer functions can be aggregated to obtain an equivalent one. Now, suppose you consider the rotor dynamics. Okay. Now, since this group of machines are coherent, right, therefore, all these swing equations you can add together, because omega is same, d omega 1 by dt is same as d omega 2 by dt. Therefore, all these swing equations can be added together, and when you add these swing equations, what will be the equivalent inertia constant? It will be sum of the inertia constants of all these machines. Therefore, this is equivalent inertia constant. Now, when I want to replace, say, the excitation system models by the equivalent, now here what is the input to the excitation system? Can you tell me? Suppose I try to write the transfer function model of excitation system. What are the inputs? We have V reference and terminal voltage. We have V reference and terminal voltage. Now, all these machines have the same terminal voltage, because they are connected to the same bus. You understand this point? All the machines have the same terminal voltage, right. Therefore, the input to the excitation system of each of the machines will be same terminal voltage, and therefore, now you can obtain an equivalent excitation system, right, because the input is same, and you can aggregate all these models. Similarly, if you take the power system stabilizer, input to the power system stabilizer is going to be delta omega speed deviation, and since the speed deviation is same for all the machines, therefore, we can find out the total stabilizing signal by adding the transfer functions of all these individual machines and considering the same input as delta omega. Now, this exercise where you replace the turbine governors by equivalent turbine governor, excitation system by equivalent excitation system, the power system stabilizers by equivalent power system stabilizer, right. For this what we have to do is that we first assume the model of the equivalent component, and then try to fit the transfer function characteristic with the transfer function of the total system, right. Now, the best reference for studying how the individual models can be aggregated together is given in this reference paper, that is by A. J. Germond, not this one, yes, A. J. German and R. Padmur, dynamic aggregation of generator unit models. Title is very straightforward, dynamic aggregation of generating unit models, IEEE transaction on power apparatus and systems, volume PS 97, number 4, July August 1978, then pages are 10602 1069. That is when dealing with the dynamic equivalencing, I started with these two references. The first reference was Robin Padmore as the author, identification of coherent generators for dynamic equivalence. Therefore, this paper addresses how to identify the coherent group of generators. The second paper written by the Berg and Gapurian, representation of coherency based equivalent in transient stability studies. Here he is dealing mainly with the network reduction and representation of the equivalent generator by a classical model. While in this paper actually, which is actually considered to be companion paper of this, these two papers are put together practically. They have appeared in the same year and in the same issue of the IEEE transaction, right. They deal with the two aspects. One aspect is the how to identify the coherent group of generators, and then second aspect is how to aggregate them. Now, just to inform you that these papers were written out of the EPRI project report. That is, EPRI has sponsored some research project, and at the end when the research project has completed, these two papers give the information about the techniques which they have developed. Now, just to give you one slight information that in these research papers, to substantiate the algorithm which they have developed, they have applied this to two large systems. One large system is the system of Michigan system, another is called WSCC system. In Michigan system, the number of buses is 1027 and the number of generators were 295. Okay. And for identifying the coherent group of generators, a three-phase fault at a particular bus was considered of 12 cycle duration in the first case, and the equivalent model which they obtained at the end, right, had (50) generators. Original system had 295 generators and the equivalent had only 50 generators. And out of this 50, it was seen actually that the 24 generators or 24 coherent groups had only one generator, and remaining coherent groups were 26. Understand what is the meaning of a group having only one generator? It means that machine has its own independent dynamics. It is not similar to other machines, right? And the studies were done actually that if you perform now the transient stability analysis using the equivalent, the time required was 55 seconds, and if you do for the full complete system, the time reported is 341 seconds. Therefore, this is the reduction which one gets in computing the transient stability of the system using dynamic equivalent. Similar results are given for WSCC system. Now, I want to point out one more point here. There is a last point, that is the coherency behavior depends upon the location of the disturbance, because when I discuss the definition of the coherency, we have written actually a particular location, fault or the disturbance at a particular location. And generally what is done is that suppose in a particular system I am interested in knowing the dynamics, that becomes my location for the fault, and I find out the equivalent for the whole thing. Okay. Now, sometimes you come across a situation where you find machines, say hydro machines and turbo generators be form, may be identical or may form a coherent group. In that case, generally what is done is that machines, the hydro machines are represented by equivalent hydro machine, and the turbo machines or turbo generators are represented by equivalent turbo generators. We do not mix up the model of hydro and steam turbine generators. Okay. With this, let me conclude today that we have studied the an algorithm for network reduction and also for obtaining the equivalent generator, first considering the classical approach, and then broadly we have considered that how do we obtain the equivalent models of excitation system, turbine governors, equivalent power system stabilizer and equivalent rotor dynamics, and similarly for equivalent synchronous machine. Thank you.